equation of axial flow machine. So we are right now moving from the general equations of a typical rotor, the general Euler equations of a typical rotor, to the Euler equation of axial flow machine. So we are talking specifically right now about axial flow machines. In axial flow machine, what is happening is that the flow enters the rotor axially and leaves axially. So point 1 represents the state of the fluid before it's entering the rotor, and 2 represents the state of the fluid after it passes through the rotor. So since this is a predominantly since this is a flow in only the axial direction, then we have the velocity triangle. I will show you the velocity triangle in a second for this type of machine. Now of course this is an axial flow impeller. Now the rotor speed, because you have an axial flow, that means the rotor speed at the inlet of the flow, which is at this point. For example, if you are like talking about the, like for example, let me show you here. So let me just use the eraser. So if you say, okay, here's the velocity of the rotor at this point, and here's the velocity of the rotor at this point. These 2 points are equal, so that means u2, the rotor speed at the outlet of the flow, is equal to the rotor speed at the inlet of the flow. They are both equal to, they can be represented as u sub m. U sub m's mean you are taking the characteristics of the flow velocity at the mean radius of the rotor. Now this is the axis of rotation. Remember, the mean means at the center you have a radius of the hub. Now this is the hub of the rotor, and you have what, the tip. So you have the tip and you have the hub. So the radius of the hub is measured from the center, axis of rotation. Similarly, the radius of the tip is measured from the center of the rotation. So if you want now to get u sub m, which is at the center here at this point, for example at this point, then you can say, okay, u1 equal to u2 equal to u sub m, which is the rotor speed at this middle point. Now this middle point can be calculated as r sub m, mean radius of the axial flow machine, times omega, the angular speed. Now a1 equal to a2, so the area of the flow is the this area. It is this area, and it can be calculated as the difference between the tip area and the hub area. So pi r tip square minus r hub square will get you here. Okay, now main radius can be calculated. Some literature stating that the main radius is just the summation squared of the radius tip and the radius hub. Okay, square root of the summation of radius of the tip squared plus the radius of the hub squared. In another literature, they represent it as half of the radius of the tip plus the radius of the hub. Now let's talk a little bit about, so I thought bringing this picture will actually illustrate the velocity triangle for axial flow machine. Now just remember, U represent the rotor speed, C represent the absolute fluid flow velocity, and V relative flow velocity. Now beta represent the relative flow angle with respect to the axial direction of the axial flow machines. So you have, now what is happening, of course it is different, the velocity triangle will be different whether you are, it is different for if you have power producing machine or power consuming machine. I'm so sorry, here so we are talking about power consuming machine. So if you have a power consuming machine, then the velocity triangle for an axial flow impeller will look like this. at the inlet and outlet. But if you have a power producing machine, which is in other words a turbine, the velocity triangle will be like that. Now let's explain something here, because there are it's just an ideal case. Sometimes you have I'm talking about pump here. So for pump, fan, or compressor, sometimes you have no like you assume swirl free at the inlet. That mean, okay, so this mean, what does it mean is that you are not taking into consideration the tangential component of the flow velocity at the inlet. So you are assuming swirl free at the inlet means there is no swirl at the inlet, and this mean, okay, this mean the C, so the C sub U1, if you are talking about pump, equal to 0, right? Because this is the tangential component of the of the absolute flow velocity at the inlet. Now, if we are talking about turbine, then we can, this is an ideal case. So as I mentioned here, under ideal design operating condition. Sometimes these ideal conditions assume that the swirl free at the inlet, if you are talking about pump, and they sometimes assume swirl free at the outlet if you are talking about turbine in this case. So if this is the case, then the velocity triangle will be drawn without the actually. So I'm so sorry here. It's not U. It's C sub omega W, because remember earlier in the previous slides we said that. Okay, so we said C sub omega is the one that represents the tangential component of the absolute velocity. Similarly, we need to delete this U and replace it with, okay, W. Okay, so you can, if this is the case for a pump, fan, or a compressor, we draw the velocity triangle as shown here without actually the swirl free, without the tangential component. Please note the difference here between the inlet and outlet in case of an ideal condition. So here we are having the tangential component of the absolute flow velocity, and here we don't have a tangential component of the absolute velocity. So because it's 0, we have what? We have the flow angle, the flow angle at the inlet section of the rotor equals to what? Now remember here we can say tan the flow angle here is equal to what? U1 over C1. Now in this case, because we are talking about axial flow machine, the absolute flow velocity is just happens to be equal to the axial flow velocity. But if you have, of course, if you are talking about a power consuming machine, then you cannot say that there is no swirl at the outlet. There is always a swirl at the outlet of a power consuming machine, and the opposite is true for a turbine, as you can see here, meaning that there is no, we assume in an ideal operating condition, we assume that the flow is swirl free at the outlet of a turbine. This is why the velocity triangle here is missing the tangential component. Now if you want to draw the velocity triangle of an axial flow impeller, you always start with the rotor speed at the inlet, which is U capital sub 1. 1 means inlet, and then you draw what? You draw the relative, or you actually draw the absolute flow velocity, and then you close the triangle with the relative flow velocity. Now the angle for an axial flow machine, the flow angle is the relative flow velocity is making an angle of beta sub f1 we call it beta sub F1 with the absolute flow velocity. And similarly for a turbine, the flow angle is making is an angle with respect to the rate of flow velocity. Okay, so in this case, what do we have? If you are talking about swirl free flow at the inlet, then the flow angle at the inlet to the rotor is equal to the plate angle at the inlet of the rotor. Okay, so with that being said, if you are assuming swirl free at the inlet of a pump, fan, or compressor, then the energy equation, the Euler equation will be just C sub omega 2 U2, which has a higher number relative to the case when we have swirl free at the inlet. When we have, sorry, swirl flow at the inlet. And here's that for the turbine. So just understand that sometimes we may say under ideal conditions that the flow is swirl free at the inlet for a pump, fan, or compressor, and sometimes we say that the flow is swirl free at the outlet of a turbine. So just be aware of these, and if this happens, then the corresponding maximum energy transfer is this guy for a pump and this guy for a turbine. Okay, now let's take an example. With this example, we will clarify the theory that we have went over. So let's assume that we have an axial flow fan. Of course, if you are talking about an axial flow fan, then the rotor will look like this. Okay, this is the axis of rotation, assuming that this is the axis of rotation. It's called axis A. Now, what is happening is that, of course, the rotor will be something like this. I mean, yeah, this represents again the radius, the hub, radius of the hub. Okay, and then we have the radius of the tip. So the radius of the tip, radius of the hub, gives you what? Gives you the flow area. So the flow area is this, just to represent the problem in a graphical context. And similarly, the other side is just a mirror, meaning that you can basically do it like this. Okay. Okay, of course, here from here to here, it represents the radius of the hub. From the axis of rotation to the tip, of course, this will give you the radial direction from the axis of rotation to the tip of the rotor. Okay, so what is the problem is asking about? It is the problem is giving you the radius of the tip, 24 inch, and it's also giving you the radius of the hub, 10 inches. So the difference between that is 14 inch. So that means the radial, the distance from here to here is how much? It is just 14 inch, which represent the radius of the tip minus the radius of the hub. So it is 14 inch. Okay, and so, and it is also this rotor is rotating at a speed of 1250 rpm. If it delivers, the problem is telling you that if this rotor is delivering a total head of 10 inches, so let's say that the head represented as H here is 2 inch of water. So because fan is used with what? Fan is usually, it handles gases, or more particularly it handles air. You need to convert this total head from 2 inch of water gauge into 2 inch of air gauge. Of course, you are giving here the flow rate, the amount of the flow that goes from this guy to here. Okay, So the amount of the flow that goes this way. Okay. Sorry, the yellow is not that clear here, but I hope you get the picture. Now, what is the problem is asking you is that it is asking you about to estimate the leading and trailing edge plate angles. So the leading edge at the flow entrance, we call it here beta, for example, beta sub B1 and beta sub B2. Okay, so okay, here's the thing. Now, because this is an axial flow machine, the first thing that you need to do is to calculate the characteristics of the flow at the mean radius. So remember, in our previous slide, I told you that the mean radius is just a square root of the radius of the tip square plus the radius of the hub square over 2. Now this you do this and you get the mean radius at about 1.53 feet from the axis of rotation. Okay, so right now, where's the mean radius? If you were to be asked, here is the mean radius at this point, more or less. This is the mean radius. Okay, so what else we can have? Now we know that once we calculate the mean radius, we can get the rotor speed at this mean radius, which is basically pi n over. Now pi n over 30 will times what is this? This is the mean radius. This will give you the u sub m. It's about 200 feet per second. The area of the flow is this guy. Okay, now why are we having 144 here? Because we are converting from inch. Remember, the 1 foot and 1 foot we have how many inches? We have 12 inch. Okay, so if you want to do, for example, 1 foot square, then you need to take the square of the 12. This will give you 144 inch. Okay. So remember, from the velocity triangle we said that here the velocity triangle we said because we assume swirl free at the inlet. In this case we have the absolute. Now here's the thing, in this example, unlike what I have explained in the previous slide, the absolute flow velocity is denoted as V. In the previous slide, the absolute flow velocity was denoted as C. Okay, just be careful of that. Now again, the flow is making an angle of beta sub F1 with respect to what? With respect to the absolute flow velocity, or in this case the axial flow velocity, because the axial flow velocity is just equal to the absolute flow velocity, whereas at the trailing edge it is not equal to the absolute flow velocity is not equal to the axial flow velocity. We have, this is the axial, the flow velocity or what. Now from this geometry we can get the relationship between we can get actually here W denotes for the relative flow velocity, so tan beta f sub 1 is equal to um المقابل على المجاور, so um over v1, or in other words the axial flow velocity. Now the axial flow velocity is just because it's an axial flow machine, it's just the total flow rate over the area. Now with this you can calculate again, because it's a swirl free at the inlet, the plate angle at the entrance is happen to equal to the flow angle at the inlet. Okay, so we get the beta plate, the angle of the plate at the trailing edge. I'm sorry, at the leading edge. So this is the plate angle at the leading edge, 65 degree. Now from the ideal order equation, if you remember, now this is the main point, the main purpose of having this equation is to get the head of this fan in terms of air. So H sub A. In order to do that, you need to utilize the density rho of water over rho of air times the gravitational aspect, and then all of that should be multiplied by the head of water. Okay, you do this. The main purpose of this is to convert from head of water to head of air. Okay, so in order to do that, just use the density ratio between the water and air, and okay, from this we actually we can get the head of air. Okay, and then why are we having this? Why are we having this? So because we want to equal this one with what? With the Euler equation. So remember, here we are dividing by the gravitational aspect. So G with G will go out. So if I get G over G, okay, and then that will equal to what? Will just equal to UM, which is the rotor speed at the main radius, multiplied by the tangential component of the absolute flow velocity divided by the gravitational. This is Euler equation for what? Basically for a fan. When you do this, you get what? You get the head of air, and then from that you can calculate the flow angle at the outlet, okay, with respect to the axial direction. Now an axial flow fan, another example is talking about an axial flow fan with tip and hub radii of this much, 0.6 and 0.25 meter, rotating at this speed, and it's giving you the total head that this fan deliver is around 5 centimeter, flow rate of cubic meter per minute, this much. Now it's asking you to estimate, similar to the previous example, it's asking you to estimate the leading and trailing edge plate angles at the main radius. So the first thing is to calculate the main radius. This one is very similar to the last one. Then you do the rotor speed at the main radius. You get it about 60 meters per second. You calculate the area, and then you calculate the axial flow velocity, and then you get the flow angle at the leading edge. And from ideal Euler equation, you do the same. You get what? Now this is from the velocity triangle. What does this guy represent? If I asked you, what does this guy represent? minus. So minus VA2 times tan beta fluid 2 is just the square velocity at the outlet. So this it represents the square flow velocity at the outlet. It is this guy. So for example, we can denote it as VU sub U2 here, this much, okay, and it is just the difference between and this guy. So this guy this is the axial flow velocity, the dashed line. Now remember, this is tan beta fluid 2. how much is it? المقابل على المجاور. What is المقابل here? So basically the المقابل is how much? So minus VU2 over over the المجاور, which is the axial flow velocity at the trailing edge. So you get this like um minus vu2 equal to tan beta fluid 2 times the axial flow velocity at the trailing edge. So of course right now we say vu2 is equal to how much? minus va2 10. Sorry, it's kind of hard to write here. So basically vu2 will equal this. Okay, so I hope you understood how did we get this minus va2 tan beta fluid 2. Now if you get this minus va2 tan beta fluid 2, of course, because we know the and you can from this you can calculate beta fluid 2, because remember this term is also equal to g times the total head of the air, which is given here in terms of as a water head. So you need to convert this to an air head first and then multiply it by the gravitational acceleration, and then you made this equal to this guy. So you make this guy equal to this guy, and since you know a u sub m, you can easily, and of course you know v sub a2, you can easily determine beta fluid 2 to be around 63.5 degrees. And